So let's start the lecture. Let me recap like what we have discussed in the last lecture, right? So we talked about asynchronous model of distributed system and the how we measure time in terms of causality, right? Causal ordering between events. So in an asynchronous system, so basically we've discussed that each machine operates on its own clock, and naively comparing events across different machines, the timestamps of events across different machines would lead to some causality violations. Like although it might lead you to convergent state, it might lead to a causality violation, right? So as an example, we showed this particular execution. We have three. Let me highlight. Yeah, we have three not replicas. Sorry, we have three machines. Each of them basically maintaining a copy of a state, the key value state, mapping key x to value 4. So we have at some point R1 decides to broadcast sets to setting value of x to 5, right? And so it when the message reaches R2, so at this point, so then R2 decide so not R2, sorry, R3 decides to broadcast setting the value of x to 6, right? And so the first time when R1 broadcasts, the time the local time is 20 there, because of clock skew and other reasons, because each machine has its own clock. When R3 broadcasts its message after receiving R1's message, the time there is, however, 15. So if you actually see if these messages actually reach R2, and R2 just compares the timestamps, right? So it would make the write of R1 bin. So the setting of value x to 5 of R1 bin instead of R3. So which is essentially will violate, it looks like a violation of causal order, right? So because the write from R1 actually precedes the write from R3 in causal order. But if you naively take timestamps, you essentially end up violating the causal ordering between the events. And this is something which is noticeable, and that's why just naively comparing timestamps is bad. Okay, so I want to basically write this out in a timeline view, right? So timeline view is where we have, let's say here we have three machines, R1, R2, and R3, right? And so when we have different machines, right? So timeline view is essentially where we show timelines for each of the different machines, right? So time actually progresses forward for each of the different machines. For example, if you have an event E1 on R1 and event E2 on R1, so you can definitely say that E1 has happened before E2 because it's a single timeline. But if you have an E3 here, so we cannot really compare the timelines of E1. We cannot say the ordering of E3 with respect to E1 and E2 because essentially they are on a different timelines, right? So it's important to remember that despite the although you might that the timeline view, the diagram might make it look like E3 has happened sometime between E1 and E2, you actually cannot really compare these events. So yeah, so if you write down that particular execution on this timeline, right? So you have initially the value of x is 4 everywhere. So let's say we are time stamping each of the values with the last write, the timestamp of the last write that actually wrote that value. So let's initiate 0, right? So at some point R1 has decided that setting of R1 x has to be set to 5. So let's say at this point of time, the time is 20 here, right? So let me just erase this one. 20, and so it reaches R3. Let me erase this. And at some point, it reaches R2 here. So it sets x to 5, 20. So here, then again R1, so here x set to 5, 20. But then R3's clock itself is at 15. So when R3 sends a message to setting 6, it is timestamped at 15. When it comes here, the 15 is compared to 20. Since 20 is greater than 15, you still have x set to 5 with the 20. Right? So this is essentially a timeline view of the same execution we had before. So okay, so this is as I mentioned, it's a you can see the loss of the violation of causality because clearly if you look at the diagram, right, so you can trace the causal ordering from x setting to 5 to and x being set to 6. So you can, looking at the execution, you can clearly say the x being set to 5 causally precedes, that is happens before x being set to 6. So you would expect x being set to 6 to take precedence over x being set to 5. And the value at R2, you expect it to be x being set to 6. But however, you have, because of timestamp comparison, you have violation of causality. So what here, it only shows up as a loss of a right? So essentially your right of x to 6 essentially just vanished because it, you did not really take into account the causal ordering. But there are more interesting violations that are possible, right? I mean, the causal violations could be even more subtle and even more like interesting. So let's consider a violation. Did anyone
I
ask
was
a
just
question?
wondering whether I just want to make a comment on the figure. I think there was an error from R3 to R2.
Oh, really? Okay.
The x tends to 6 at 15. That message is not reaching R2, right? Means you have annotated it as x tends to x is set to 5 at 20.
No, that's the actually, it actually, even if it reaches there. So let's say, okay, so here when it is x set to 5, right? So its timestamp when it was set is essentially 20 here, right? Because the timestamp of the write that has set x to 5 is 20. So when you write x to 5 on R2, the you store the timestamp of that write as 20. The last write that has written to x has a timestamp of 20. Now, when x is set to 6 from by R3, since R3's writes timestamp is 15, right?
Yeah.
So when it comes here, so let's say you have a write that actually reaches here. So you have the current value of x is set to 5 has a timestamp of 20. The new write that is being, that you just received has a timestamp of 15. So R2 is correct to think that the write that it has just received is an older write, and if it's only comparing timestamps, it would just discard that write and just keep the write that it had initially had it in its position, right? Do you
Oh,
understand?
no, no. I was just confirming whether the annotation on the message from R3 to R2, that should be x right to 5 at 20, or should it be x right set to 6 at 15?
So I guess the notation, so here let's say, okay, so you say this, you get 15 for instance, right? So this is, but
Yeah.
here the local write of x to 5 already has a timestamp of 20, right?
Okay.
So which one would you think, if you're comparing timestamps, which one takes precedence if you just compare timestamps?
Yeah. The x set to 520.
Right? So you essentially, this gets vanished, right? So the write is lost.
Okay.
So that's the
Oh,
reason why we have actually annotated it with the text set to 5.
oh, okay. Okay.
Yeah. So okay. So this is one violation of causality where you actually just see the loss of rights, but there are interesting ones as well, right? So there is this one that I've in the context of a social application. There's one example that I took from Baylis et al.'s Sigmod 13 paper. So here is one. So let's say you have 3 users, right? I don't know, my lines are somewhat screwed up. Actually, if you have a special feature here, yeah, that's correct. Okay, so let's say you have 3, separate users, right? So let's say you have Sally and James and Henry, right? So let's assume that these are, when I say these are users, essentially these are machines that are connected to which these users are connected to, for instance. And let's assume this is a social application, let's say a chat application, right? So at some point, Sally might say that, oh my God, so her son Billy is missing, right? Um, and at a later point of time, so she discovers her son Billy is in fact out there playing in the playground. She says, oh no, false alarm. Billy is playing out outside, right? So let's say you have, let's look at James' timeline. Right? So let's say James first initially receives this message. Simple. So this is the receiving of that message. And then you have then receives this message that it's a false alarm, and essentially types a new message saying, oh, good to know, and what a relief, right? Now let's look at Henry's timeline, right? So let's say if, Henry actually got this message, this point, but this message while it's still in flight, whereas I actually got James's message before. So to Henry, it looks like Sally typed, "Oh my God, Billy is missing," and then James essentially reacted with, "Oh, what a relief!" Right. So you have essentially, the timeline is, this message here, and this message here. So, so yeah, so this actually is, a violation, and another interesting violation of causality, because you actually, the for the message, for James's message, right? James's message causally depends on both of Sally's messages, right? Whereas the order in which they are applied on Henry's machine does not actually respect the causal ordering, because let's say this, let's call it, this is M1, this is M2, and let's say this is M3, right? So you have M1 causally preceding M2 preceding M3. Whereas on Henry's machine, you only see M1 and M2. So while M3's dependencies are both M1 and M2, since you only see M1 and M3, so not all M3's dependencies are applied on Henry's end. You actually see a violation of causality, and this actually manifests in a somewhat interesting way, right? Okay, so any questions about this example? Okay, so there are other interesting examples as well in the context of social applications. In fact, this violation of causality, in fact, does happen very rarely in practice, in context of social applications such as Facebook and so on. So yeah, so these are just an interesting example. So yeah, the summary is that in the absence of a consistent global time, we actually, if you just use timestamps to order things, order events across machines, you end up seeing a violation of causality, right? So yeah. So what else? Okay, so we have seen here how causal ordering actually works between various particular messages, right? But causality is not a complete order, because it's not the case that every pair of events are causally related, right? So let's take another distributed execution, right? So let's say you have three replicas or three machines. You have R1, R2, and R3. So okay, let's say we have a send event A. A gets the message that is sent at A gets received, and let's, for the sake of completeness, let's also name the receive messages, right? So receive event, sorry. So you have receive event B here, and then something gets sent from R2, let's call it C, T, and D precedes. So after the receive event of T, you actually have send event of E, and E gets received here. Let's call it F. And before D and D, let's say you have R3. R3 has a send event. where G gets received here. Let's call this H, right? Okay, so in this execution, can you name the causal ordering of events?
A precedes B, B precedes C,
Right.
C precedes D.
So, okay, so let's say, let's use happens before as a relation to denote causal ordering, right? So you have A happening before B, B happening before C, C happening before D, and E,
G happens before D.
and E happens before F, and F happens before
H.
H. What about G?
G happens before H.
Okay, G happens before H. Let's say that G happens before H. But are there any other causal relationships between G and other events?
Yeah, G happens before D.
Right. So G happens before D and E as well, right? So let's can just move it a little. Okay. Okay. So you have G happening before D. Okay. G happening before E. What else? So if you know that G happens before E and E happens before F, can you say something of the relationship between G and F? Yeah, so G happens before F as well, right? So if you, let me write it down more cleanly. So you have, let's say you have, for the same diagram, so you have A and B and C and D, E and F, that's it, right? And H and H. And you have G and D and F. So, we have these relationships as well. So each of these arrows happens before arrow, right? So this is happens before and dot dot. So what is the relationship between the events A, B, C, and G?
There is no relation, I think.
Sorry?
There is no relation.
There is no relationship, yes. So how are A, B, C, and G related? They are not causally related, right? So events A, B, C, and G are not causally related. So what does it tell you about causal ordering as captured by happens before, right? So happens before, as it is, as we have described here, it's not a complete ordering, right? So essentially, causality, unlike a physical time, which is essentially, if you measure events as per the physical time, you get a total ordering of events, right? You can always compare two events and say, oh, either A happened before B, or after B, or maybe at the same time as B. But with when you have this notion of time that is captured via causality and not as using a physical clock, right? So you have you measure time using this relation as, for instance, happens before, where you cannot really, and it's not always the case that you can order two particular events. You can have two events that are not related by happens before relation, so that they are not causally related. So that's something which is very important to remember, right? So let's say for, now let's formalize whatever we have discussed, right? So happens before relation. Okay, so let's say we have E be the set of all events in a distributed execution. So if E could, for instance, include both the send events and the receive events, right? So in this example, I've actually marked both send and receive events. So A is a send event, B is a receive event, and so on and so forth. Okay, so what's the first property of app? Let's use HB to denote happens before relation, right? HB. So what's the first property of HB? What's the domain of HB? It's E. So HB is a subset of E cross E, right? So what's the another property of HB? So you have seen, from given this diagram, right? So you're given this execution. What can you say like is is a property of happens before relation? So here we have, in this particular example, so we have said that G happens before D and G happens before E. But where did the arrow G happens before F come from? Because we implicitly assume happens before to be a transitive relation, right? So we have happens before is a transitivity, which means that for all E1, E2 belongs to E, or we have a third one, sorry, let's say we have E1, E2, E3. E1, E2, and E3 belongs to E. Happens before of E1, E2, and happens before of E2, E3, essentially implies happens before of E1, E3, right? Do you agree with this? So happens before is a transitive order, because if A happens before B and B happens before C, you actually have, you can say for sure that A also happens before C. Okay, so like transitivity, what else is could be said as a property of happens before relation? So if you remember your discrete mathematics course from your undergrad, so there are these properties we ascribe to relations, right? So symmetric, anti-symmetric, reflexive, and so on and so forth. So among those, do you recollect any other property being applied to happens before?
I'd say anti-symmetric.
It's anti-symmetric, great.
Because if you have two events, either one happened before the other, or you can't compare them.
Right. So how do you
have like a circle?
How do you propose a right anti-symmetric thing? So let's say I have for all E1, E2.
Yeah, I guess for all E1, E2,
Right.
let's see.
So happens before.
You'd say E1 happens before E2,
right.
Implies, or I guess you could just say not E1 happens before E2, and so in parentheses
Or
happens before E1, E2.
So you're saying something like this, right?
Yeah. But I guess then you could say the exact same thing reversed again, or you could just say not, and then in parentheses happens before E1 and E2, and happens before E2 and E1.
Okay, so essentially you are proposing an alternative way of writing, which is if E1 it cannot be the case that both E1 happen before E2 and E2 happen before E1. So which essentially becomes equal, like which is another way of saying the same thing, right?
Yeah.
So let's say stick with this first formulation, right? So usually the way anti-symmetricity is written in conventionally is if you write it in a conventional fashion, I would have to write this happens before E1, E2 implies either it's not the case that E2 happens before E1 or E1 equal to E2. So that's usually what happens before, what anti-symmetricity usually means, because, if relation R relates A, B, and B, A, then it must be the case that A must be equal to B. So that's how it's usually written. But here, however, we do not write this formulation because we assume, or like another property of happens before is that it is irreflexive, right? It is for any event E, it is not the case that E happened before E. So this point of A equal to B, when if A is related by happens before to B, and likewise like B vice versa, then A must be equal to B does not come up, because it's never the case that happens before relates the same event to itself. So so yeah, we have written down like few properties of happens before, which is transitive, antisymmetric, reflexive, right? So let's keep this aside for a while, and let's for the sake of comparison, let's look at another a very familiar relation. Let's say we have a less than relation between natural numbers, right? So let's keep it aside, and so let's consider less than relation. So less than is also a binary relation like happens before. So less than it's over n cross n. Let's say it's over natural numbers. So I won't write it down, but it's transitive as well, right? Because if A is less than B and B is less than C, then of course A is less than C. It is antisymmetric, because if A is less than B, then it cannot be the case that B is less than A. And it is a reflexive, right? Because a number cannot be less than itself, right? So these properties, like all the four properties, are common between less than relation on natural numbers and happens before relation that we have defined our events, right? So then are both of these comparable, or is there any difference between happens before relation that as we have defined it, as we have seen in the examples, and a less than relation over natural numbers?
Well, yeah, I mean, less than on natural numbers provides a total ordering, whereas this doesn't.
Yeah, exactly, right? So we have less than is a total order, which means that for all natural numbers n1 and n2, either n1 is less than n2 or n2 is less than n1. So this is what is basically a total ordering, right? Totality. So these basically this the first is the domain property, but the remaining four together imply that it, less than is a strict total order. Strict because if it's non-strict total order, it would have been that it would have allowed reflexivity. So irreflexive condition essentially makes it's an order because it's transitive and antisymmetric, and since it's a reflexive, it becomes a strict order. And since it is total, because it relates every pair of natural numbers, it becomes a strict total order. By applying the same terminology, what could we say about happens before relation? So we have transitivity, we have antisymmetric property, we have irreflexivity, but we do not have totality. So what would it become then? It is definitely strict because it's irreflexive, and it's an order because it is transitive and antisymmetric, but it's not total. So which means it's a partial order, right? So happens before is essentially a strict partial ordering of events, which means that it actually relates, there are pairs of relation events that are not related by, that could not be related by happens before in an execution, right? So that's essentially how we the formal definition of happens before relation. So the reason why I defined it formally is because you actually see this the happens before relation coming up often and often in describing distributed executions, right? So you have to understand like what exactly do we mean by HP relation when we say HP of E1 and E2. So this is what we mean, and this is what it's a strict partial order, and essentially it is transitive, anti-reflexive, antisymmetric, and reflexive. Okay, so okay, so let's go back to this first example, right? Let me take that and paste it here. Where is this? This one. Okay. So this is the timeline view. Copy. Let's just paste it here. Okay, so here we have not taken happens before or the causality into account while applying, while processing events, right? So in this execution, if you want to avoid the causal ordering, like this violation of causal ordering, right? If you want to essentially preserve the causal ordering of events when applying, let's say, to R2, what could you have done? How would you modify, like, let's say here we have used local timestamps, like physical time to measure time, and essentially we timestamped each message with the local physical clock. So that's where this 20 came from, and that's where this 15 came from, etc. Right? So let's say you are now free to modify your clock, right? You're not bound to a physical clock. You're now, the clock is in your control, and you can modify the clock however you want, for instance. Now, can you take advantage of that power to make this execution consistent with its causal ordering?
So I think like when R3 sends a message to R2, along with the message, it can also piggyback all the causality it discovered locally to R2. So R2 will have the current message and the message like happens before this one, and
yeah,
R2 can make like a better decision.
Could you explain that a little? I think I might have lost you.
Yeah, so like when R3 sends the message like X set to 6:15, it can also send together with the causality it discovered locally. Like
okay, so yeah, so okay, so I get your so Zhang gives a very good suggestion, right? So he says, like, when you're sending X to 6 there, right? So why don't you also mention the fact that this actually causally depends on X to 5, so that when you get X to 6, right, you know that in among its dependencies is X to 5, which you've already processed. Now that clearly tells you that X setting X to 6 causally succeeds X to 5, so you're gonna process it anyway. Good, that's a good suggestion, but how do you implement that suggestion? Let's say you're trying to implement it here, right? So how do you track, how do you make sure that X to 6 mentions the fact that X to 5 is causally preceding event?
You can change the timestamp on X to 6. Instead of 15, you can use it as 21 or 22.
Excellent, right? So you can just, you have time here, time is in your control. So you're running a clock. You're just, let's say you're running a clock, you're lazily running your clock and you're at 15. And you get a message saying, hey, look, here is set X to 5. And by the way, the time on my end is 20. Then you can immediately essentially say that, oh, okay, look, now I know somewhere in the, in my world, time has already progressed to 20. Why don't I update I update my clock and advance my time to 21 or 22, right? So since clock is in your control, you can say essentially, for instance, oh, since 20 X to 6 causally succeeds 21, I increment my clock here. So I clock plus plus, not just plus plus. Actually, you actually take you set the clock. Clock is timestamp of message, right? +1 or something. So it becomes timestamp of message is 20 and the clock becomes 21. So you label it with 21. So when this comes over here, you have essentially X to 6 with 21. And since 21 is greater than 20, this wins and everyone's happy, right? So if you have, so what have we done here? If you take a step back and see, we have actually taken the control of the clock into our own hands. And we have incremented, essentially, we incremented clocks in order to make it consistent with causal ordering, right? So this is it. I'm sorry.
Isn't it just that in some way we have made the clocks according to R1 and we're treating R1's clock as global?
Well, it need not necessarily be R1, right? Let's say we get 21 here. So let's say on R2's end, we have, if you extend this example, let's say, for instance, at some point, R3's clock has, due to internal events, it has progressed to, let's say, 28 or something, right? For instance. But due to some reason, R1's clock is still at, let's say, from 20, it has only progressed to 24. Right? Now, if you get both the events from one from R1 and one from R3 to R2, whose clock would you pick? It need not necessarily be R1's clock, right? Because now you have, forget about R1, there is someone else in your world who has already progressed to 28, right? So you might update your clock, it makes sense to update your clock to 28 and not 24 because the world has already progressed, right? So it's not just based on R1's time, but rather by picking the time, like essentially you try to take the value of the time that is most ahead in the entire, in your entire world of execution, right? Does it make sense?
True, but
Or maybe
still
hold your thought for a while.
can we
Because
change?
I'm going to explain, like this is so far I've only tried to give you an intuition of like what, how you can prevent this sort of anomalies. But this is the same intuition that underlies something called Lamport timestamps. So let me explain Lamport timestamps and maybe that will answer your question, right? Okay. So yeah, what's a Lamport timestamp, right? So Lamport timestamps are essentially, this is again, this bears the name of Lamport because it's Leslie Lamport who introduced it in his 1972 paper, I think. So the idea is to have not a physical clock, but rather a counter, a sort of logical clock, which is simply a counter that counts the events. Instead of counting the number of clock ticks or like CPU cycles or something, you just count the number of events, right? And that becomes your measure of a clock. So that's essentially the idea of Lamport timestamps, right? So to demonstrate that, let me take this this example because it has more events. And it also demonstrates a very interesting point. So let's take this example, right? Let's paste it here. Okay. Okay, so here is how Lamport timestamps work, right? So everyone starts at 0. That's initially, right? So when you have an event, when an event is about to happen, you increment your clock. So here event is about to happen, so you get +1, and you tag the event with the latest clock, which is 1, right? So the event from 1, so message arrives here. So it's a send event, right? So it's a send. So the message arrives on R2. So R2's clock, the Lamport clock is still 0, right? But it sees message from R1 bearing a clock message of 1. So essentially you take the maximum of your clock and the message's clock. So essentially on receive, let's say you have my clock, right? Which is denotes the clock on your end. So my clock is, you set my clock, it's actually an assignment, to maximum of my clock, or let's say on receiving message, this is message.timestamp +1. Is it visible? So yeah, so essentially what you do is you keep track of time by essentially trying to get updated, always to be ahead of what you think is the latest time is in the machine, in the entire setup, right? So here, once you receive the message, which is A, you know that time at 1 has already progressed, time at R1 has already progressed to 1. And since now you have a new event, which is a receive event, and you're counting receive events as well, you update the clock here to 2. So it goes directly from 0 to 2, right? And the next time you're sending an event, another event happens on R2, which is a send event, right? So on send, what do? You essentially update your clock by 1. My time is updated by just my time +1. So your clock goes from 2 to 3. Now C is a send event. So C goes to, the message goes to R3. Now R3's clock is 0 as of now. Now what should be R3's clock now, as per this computation? When you get the message, when you have at the receive event of D.
wondering if G is an event, wouldn't the clock of R3 have changed to +1?
Excellent. Yes. So yeah. So G itself is an event. So G, since if you actually from R3's perspective, when it is doing an event G, it's a send event. It hasn't known anything about anyone else's clock, so it actually can increment its clock by 1. So G has a clock of 1. Like G has a timestamp of 1, right? And its local clock is 1. But then the message at some point message from R2 arrives, just the message that is tagged with C, right? Which has a timestamp of 3. So it arrives, and that's the receive event corresponding to that message is D. And what happens at that point?
So it will be the max of 1, 3 plus 1.
Which would be?
So 4.
Right? So you have timestamp of, we essentially, the current clock at R3 gets updated to 4. Why? Because at that point, R3 knows that someone in the world, in the participating world of distributed systems, so like here in this execution, have advanced their clock to 3. So the clock is at least 3. Like they try, as I mentioned, the aim of Lamport clock is to essentially catch up with whatever is the latest time that is known in the system. So you have, you know that the latest time is already 3, and since you now have a new event, and your clock essentially counts the number of events, you increment your clock by 1, so just 3 plus 1, 4. So that becomes 4. Now, when the send event E happens, what does R3 know? R3 knows its local time clock is 4, right? And it hasn't known anything better since then. So it would then, since it's a new event, it increments the clock by 1. So clock becomes 5, and the timestamp of the event E, which is a send message, becomes 5. Now 5 comes here to F. What would be the timestamp of F?
Will it be 6?
Sorry?
Will it be 6?
6? Okay, yeah. So because again, the same logic, so the R1 as of now has its local time as 1, and it has not known anything better since that point. But now it got a message saying, hey, local time, time somewhere has advanced to 5. So it tries to catch up. So it makes its local time as 1 plus that, because it's a new event, it's a received message, it's an event. So it's 1 plus the latest known time, which is 6, right? And what happens with H? Now H is an interesting perspective. It's an interesting case. What would be the time after R1 processes H, which is the receive event corresponding to send event G? Take a shot. Anyone?
It will be 7.
It would be 7. Yeah. Why is it 7? Why is it not 1 or 2?
Yeah, because of the equation on the right. So it will be the max value of current clock 6 versus 1 from the message plus 1. So it will be 6 plus 1, 7.
Yeah, no, that's correct. But can you give an intuitive reasoning, like why it should be 7? Like intuitively from R1's perspective, why it should be?
So because F happened before H from R1's perspective. Oh wait,
Yeah.
no.
No, yeah, that's correct. That's also correct. So the thing is, if you apply the same reasoning at R1, right? So R1 knows the current clock, the clock of the world, like somewhere, like for the entire system is at least 6. Like at least 6 events have happened so far, right? And now you get a message saying, hey, my timestamp is 1, which means that the message might have originated when the time at that machine was 1. But you know better. You as R1 know better that the time has already progressed to 6, right? So you don't take the timestamp of the incoming message, you just increment your own local time. So that's how 6 becomes 7, right? Does that reasoning make sense? Nick, what do you think?
I think it makes sense in the sense that the point of these timestamps is to at least imply causality. So
Right.
if you've just received this message, you definitely want your timestamp for receiving it to show that it depends on the send event. And so if it's 7, that's greater than 1. So all good.
Right.
But then you also want to show that it depends on anything that has happened on your local time stream. So the best. So if it's 7, it's greater than 6. So that is also true. So just from this timestamp, you can't maybe see the precise causal order, but it's at least implying the causal order.
Very good point. Excellent. That's going to be my next statement, right? So if you look at the causal ordering of events, right? We have already written down the causal ordering of events on that. Let me take that out here, right? So let's just copy this. Copy and just paste it here. Something. Copy. Paste. Okay, good. Okay, so let me try to make the entire screen visible for you. Okay, maybe that's good enough. Okay, so let's now number these events, right? So A, we know the timestamp is 1, B is 2, C is 3, is 4, 5, 6, and 7, and G is also 1. So from this, what can you infer? So this is this is diagram that we have drawn before we talked about this timestamps. So this actually represents the causal ordering of events, right? So here, from this numbering scheme, we can observe the following. Let's say for any event A or E, let TS of E denote that timestamp or the Lamport timestamp of that event, right? So when okay, what can we say about the relationship? Let's say there are 2 events. There's E1 happens before E2, right? And then timestamp of E1 and timestamp of E2. So how do we propose a relation that relates all these 3 things?
I had one doubt in this in the example. Like if I look at B, C, and G, so I can also see that G causes B and C. And if I just
didn't
look
say
at the
that. I mean, so that's why we are here, right? So we have so far, we have given a numbering scheme, right? I have made no claims about how it relates to causality yet. That's where we are in. Okay. So we have given a numbering scheme. So I call it a Lamport. That's essentially the scheme that Lamport has proposed. Okay, we call it Lamport timestamp. So what is the relationship between Lamport timestamps and the causal ordering between events? So that's what I'm asking. You are proposing that essentially whenever, if I articulate your point and you generalize it, you're essentially saying that if timestamp of E1 is less than E2, then it must be the case that E1 happens before E2. That's what you're proposing, right? Is that correct?
Yeah. No.
No or yes? Sorry.
No. No,
okay.
It's not correct.
It's not correct. Okay, good. Then what is correct? So the only thing we can say from this diagram, and this diagram essentially represents the causal ordering of events, and also I've given the timestamps for each of the events, right? So if you see, the only thing that's true from this diagram is whenever E1 happens before E2, then timestamp of E1 is less than timestamp of E2. So for all E1, E2, if E1 happened before E2, then the Lamport timestamp of E1 is less than Lamport timestamp of E2. Is the converse true?
No, the converse is not true.
Converse is not true, right? Because
that's basically okay, because if you think of the 2 situations, 2 events are either causally ordered or they're not.
Mm.
And so basically when we were talking about the causal order, like anomalies and things, we want to do a specific thing when they are in causal order, but we don't really care what we do when they're not in causal order.
Right. Right. Essentially, so as Nick mentioned, so essentially the converse is not true, which means that when timestamps are, if a timestamp of E1 is less than E2, then it need not necessarily mean that E1 happened before E2. It could have been the case that E1 has happened concurrently with E2, right? And which is what happened here in the above execution. So G has a timestamp which is less than two B and C, but there's no relationship between B and C and G, right? Because they're essentially, they happen sort of concurrently. There's no happens before relation between them. So to state it in the contrapositive ways, essentially, if you write it, essentially, if whenever P implies Q, then it should not Q is implies not P, right? So if you take that and apply here, essentially all you can say is whenever timestamp, if timestamp of E1 is not less than timestamp of E2, then it cannot be the case that E1 has happened before E2, right? So that's all you can say from Lamport timestamps. If timestamp of E1 is not less than timestamp of E2, that is, if let's say if it's greater or equal to timestamp of E2, then it cannot be the case that E1 has happened before E2, right? So that's all you can say from Lamport timestamps. But still, it's sort of a first measure, a simple measure of causality, because at least it lets you avoid examples such as the one we discussed before, the X set to say 5 and X set to 6. Had you used Lamport timestamps there, which is what we have done essentially to fix that problem, you've incremented time from 20 to 21, right? So you could at least avoid those sort of situations, right? So to summarize, essentially, Lamport timestamps are consistent with causal ordering. I say consistent because they do not, because of this, this thing, right? If E1 less than E1 happens before E2, then of course timestamp of E1 will be less than timestamp of E2. However, it does not characterize causal ordering, because the other way, the converse is not true. Do not fully characterize, let's say. Characterize happens before causal ordering. So is that clear? That's an important distinction to remember, because the next is, okay, so far we have given a numbering scheme which is consistent with causal ordering, happens before relation. Great, we have made some progress. Now, but we only made partial progress because our numbering scheme did not entirely characterize happens before causal ordering. We need something better, right? Okay, so let's go there, right? So okay, so next, what would be the next advance? So what would be the next step? Next step would be a timestamping scheme that fully characterizes causal ordering, right? How do we go about that? Now I'll give you a hint. Here we have, if you look at this thing, right? So here we have used less than relation on the right hand side, whereas on the left hand side we have happens before relation. Now, as we have discussed before, what is the difference between a less than relation and a happens before relation?
The less than implies total ordering.
Yes.
Or yeah.
Yeah.
And that happens before just those partial ordering.
Yes, excellent. So less than is a total order over natural numbers, and timestamps are natural numbers as we have defined here. Whereas on the left hand side happens before is a partial order. Did I say it right? So right hand side, the less than is a total strict total order, and happens before is a strict partial order. So using just less than relation over natural numbers, you can never characterize a happens before relation, which is a complete, it's a partial relation, it's a partial order, right? So do I make sense? So using, you cannot characterize a partial order with a total order, right? So in order to characterize a partial order, you need a partial order, right? So on the right hand side, you have to replace the less than relation over natural numbers with something else. So that's the hint. So how do we do that? Is the question. Okay. So okay, we need a partial ordering relation to characterize less than happens before relation. So less than over, okay, less than n cross n is a total order, right? So can you give me an example of a domain for which less than could be a partial order? Or just, forget about that, just for any domain, give me an example, a couple of examples of partial orders. Apart from happens before, of course, we have discussed happens before, but or simple data structures such as natural numbers or sets and so on. What is an example of a partial order?
Well, like on XY coordinates, if you just order by one of the coordinates. Very
good. Yeah, excellent, right? So if you have Cartesian coordinates, so you have x1, y1, and x2, y2. So you can define a less than relation wherein only x1, the pair is less than the other pair only if the corresponding components are less than each other, right? So one is less than x2 and y1 is less than y2, right? So now less than over, let's say this is nn cross nn, right? Or pairs of natural numbers is a partial order, right? Why is it a partial order? Because if you consider two, let's say it's 3, 4 and 1, 5, right? You cannot say anything about these two pairs. Neither is 3, 4 less than 1, 5, nor is 1, 5 less than 3, 4. So it's a partial, they are not related. So in that sense, it's a partial order, right? So by making a domain from natural numbers to pairs of natural numbers or tuples of natural numbers, we have and by still retaining the less than relation, we got into a partial order, right? Now tuples of natural numbers is what can essentially we can also call them as vectors of natural numbers, right? So that's a hint. So essentially, by using vectors of natural numbers as timestamp and not just simply a single natural number, you can get a partial order which has a hope of completely characterizing happens before relation, right? Now with that hint, let's go ahead and try to arrive at that vector of natural numbers as a timestamp, right? So let's go back to this example and let's paste it there. Maybe I'll take the original one. Where is that? Yep, it's here. Copy. Would it fit here? Just leave it. Let me scroll down. Okay. Good. Okay, so there, if you look at the numbering scheme that we had, the single numbers for this example where we used Lambo timestamps. So we had so natural numbers where we have given the number 1 to G and also to A, right? Now, in order to differentiate between them, right? how could we differentiate between this one, like R1's 1 and R3's 1? So you could simply say, for instance, that this is, you could tag the number with also the number of the machine where it originated, right? So this could be, for instance, 1's 1, and this is, for instance, could be 3's 1. Let me write it down so that it's clear. So this is 1's 1, and this is 3's 1, right? Now, if you represent it as a tuples, it's 1 1, and this is 3's. Actually, no, that's a bad example. Let's since we have 3 machines, right? Let's say we represent it as a triplet. So you can say this is 1's 1. We have 3 places here. Since this is 1's 1, you write 1 here, but you leave the other 2 blank for a while. And since this is 3's 1, you write 1 in the third position, and you leave other 2 blank for a while, right? Now, clearly, these two are incomparable, right? I mean, modulo what you write on the other remaining 2, but naturally, it's not the case that a pair that has last component of 1 is always equal to the pair that has a first component of 1, right? So we have, by essentially differentiating, by giving different positions to different machines, right? You can essentially differentiate between events. So that's the idea behind what is called a vector clock. This is what I tried, I gave a sort of introduction to in the last class, right? So we have, instead of having a single timestamp, you have a vector. Vector is essentially a sequence of a tuple of numbers, right? So each position in the vector represents the clock at a particular machine. So let's say I have first position representing clock at the first machine, second position representing the clock at second machine, third position representing clock at third machine, right? And each machine has a full ownership and is responsible for the clock over its first machine, or its own, the component of clock that represents its own clock. That's it, right? Whereas the other 2 components of, in this example, the other 2 components are not under that machine's control. Like, for instance, on R1 has complete control over what it can do with first component, because that is its own clock, right? Whereas the other 2 are the clocks that are, it's supposed to represent the clocks on other machines, so it has no control over. So what can R1 do with those clocks? It can only learn the values of those clocks. It cannot directly increment them or decrement them. It can only learn the values of these 2 clocks, right? Whereas for the first clock, since the first component is its own clock, it can actually modify it, right? It need not learn the value from anyone else because it has the authority, it can modify it. So that's the fun, the idea behind, doing vector clocks, right? So you have 3 numbers. So now let's actually fully work out this example to understand vector clocks. It is this, right? Let's say, again, since we have 3 machines, we have vector clock that has 3 components. So let's say everyone starts with 0, 0, 0 initially, right? Now, A does the first event, which is a send event, right? So we have, since it's A's event and not anyone else's event, which component would you increment now? Just say we are following the same scheme as Lamport timestamps, right? But now we have 3 Lamport timestamps, not 1. Which one would you increment?
The first dimension.
The first dimension, right? So you get 1, 0, and 0. So you get the message from here to here now. Now let's get to B. B is a receive event, and B has just received a message whose timestamp is 100, whereas its local timestamp is 000. What would it do? First of all, third component is the same, so and it has no control over third component, so third component is anyway 0, right? Now what would be the first and second components?
Will it be 1, 1?
Exactly, it would be 1, 1, right? Why is it 1, 1 and not 1, 0 or 0, 1?
1, the first dimension, because it's being informed by the message that it received, and the second dimension corresponds to itself, so it just increments its own clock.
Exactly, yeah. So it has complete control over second component, and it's a new event, so it increments its own clock. Whereas the first component is, it's learning the value from someone else, which is R1 in this case. So it and the learned value is greater than the current value, so it increments it to, it takes the maximum of both, right? So that's the one. So if you we'll write out the complete. Maybe I should write out. We'll do it later. But first, let's work out this example. Let's go ahead, right? Let's push further. What would be the timestamp for C?
120.
120, right? And okay, let's since G happens first here, let's go to G. What would be the timestamp of G?
001.
001, yes. And timestamp of D? Now here
122.
122. Great. Why is it 122?
I mean, it has to increase its count from 1 to something new.
Okay, so that's this part. And it learns the new components from C. So this and this, right?
Yeah.
Okay, good. Let's push further. What's the timestamp for E?
123.
Okay. Timestamp for F?
223.
Okay. So far everything has been causally, fine. Now let's come to H. What's the timestamp for H? Someone else other than Mayank, let's see.
323.
323, right? Yeah, because for the clocks component of second and third clocks, it has already known better values, later values. So it would look at the value of G's message and says, oh, G is just lagging behind. No, I'm not going to take G's version of clocks. So I'll only retain my version of 2s and 3s clocks. Whereas my own clock, since it's a new event, I'm going to increment it by 1. So that's how we got 3, 2, and 3, right? Great. So now let's write down. Now, let's take this. Let's do the same exercise as we've done before. Let's take this. Here. Okay, so now let's write down their clock values, right? Maybe I should just keep it a little. Okay. We can't keep everything in the same frame. Okay. Okay. So it's 100. B is 110. C is 120. D is 122. E is 123. F is 223. And H is 323. And G is 001, right? Okay. Now, is 100 less than 110? Oh, by the way, so let's say we relax the notion of less than, where I have defined that every component has to be less than the other. Let's say, for instance, for the time being that we take less than or equal to as well. I'm going to define it precisely later, but let's say we take, you consider pair x1, y1 to be less than x2, y2, if either x1 is less than or equal to x2, or y1 is less than or equal to, and y1 is less than or equal to y2. So if you take that definition, is 100 less than 110?
No.
Why is it no?
Since for A, the leftmost one is greater than the 0 in G, And for G, the rightmost one is greater than the 0 in A.
No, I'm not saying for one A and G, I'm basically proposing the timestamps of A and B. So 100 and
Oh. Oh, okay, sorry. Yeah, that's greater.
Yeah, right. So you can say it's
110 is greater.
Yeah. So even though these components are equal, let's say for time being, we are also taking equality. As long as there's one other component which is greater.
Cool.
So likewise, it's greater than 120, right? And so on and so forth. So you have basically less than relation between all of these, which is same as what we had during the single timestamps. But now the difference here is when can you compare G's timestamp 001 with A's, B's, and C's timestamps, which are 110. So this is A. This B is 11. Sorry, A is 100. B is 110. C is 120, and D is 122. 122, I believe, right? Yeah. So can you compare these? Actually, these. Okay, let's say we just take C. Can you compare timestamp of G with A, B, or C? You cannot, right? So there is no less than relationship between timestamp of G and timestamps of A, B, and C, right? So now there is, we have actually a partial order that is capturing the causal ordering of events. So whenever timestamps are comparable and less than, like timestamp of event 1 is less than E2, it is the case that event has a need happen before E2, and the converse is also true, right? So by extending Lamport timestamps to vector clocks, we actually have got into a partial order that completely characterizes the partial order that we have, which just happens before order. So, the summary is that vector clocks, vector clocks essentially partial order completely characterize causal ordering, right? So do you agree with the statement? Okay. So you essentially by we started with Lamport timestamps, and then we have actually upgraded them to vectors instead of scalars, thereby inducing a partial order. And we have now defined partial orders in a way such that we could completely characterizes the causal ordering of events. So we now have a numeric metric, an actual metric to measure to order events as per causal order, right? So this is very important, and that's why vector clocks are very, very useful in practice, even in practical distributed systems. So if you look at in any of the practical versions of distributed systems that provide causal guarantees, right? They actually use vector clocks internally. So even there's this paper called Bolt-on Causal Consistency from 2013 by Bayes et al. I think that's the paper I referred to before. So they propose, so essentially they show that given any eventually consistent data stores such as your Cassandras and so on, you can always make them into a causally consistent store by essentially cleverly manipulating vector clocks among various versions and various replicas of the database. And so vector clocks are really, really useful in practice and also in theory. So this is what essentially entails, essence of vector clock is, right? Okay, now that we have vector clocks, now let's, how much? Can you stay for 4 more minutes, let's say? I just want to show one example. Okay, so let's go back to that Sally example, right? So where is this? Yeah, this one. Now, can you use vector clocks to rectify the situation? Or maybe I'll leave it as an exercise for you guys, right? So I want a scheme wherein I want to use vector clocks and rectify this particular problem, wherein Henry, when Henry receives a message, or Henry's machine receives a message, water relief, right? And oh my God, Billy is missing, right? Henry's machine should know that there is one more message that is missing between these two messages, and Henry's machine has to wait for that message. How do you propose to do that with vector clocks? So that's the question. I leave it to you as an exercise. Let's discuss this, maybe you can propose me solutions in the next on Tuesday, right?
I had one question in the sense that, like, doesn't this mean that Sally needs to know that she's only going to be talking to James and Henry? Like, every process needs to know how many other processes are involved.
Very good question. So that's the fair criticism against vector clocks, right? So vector clocks assume that you actually know how many components exist and how many, like you have to know how many components must be there in a given vector clock, right? So you must know how many machines participate in this process. So there are ways you can actually, let's say you have, instead of using a simple vector clock, you can have a hash map, and each machine, assume that each machine has a unique identifier, right? So if you have 64-bit UUID, for instance, then you can use hash map to map the 64-bit UUID to its own clock. And so whenever a new machine joins, you assume, you can make fairly an assumption that the UUID has never been used. So that clock is anyway set to 0. And now the machine uses the clock that starts at 1, right? So you can, by extending this tuple to essentially a hash map of UUIDs and so on, you can extend this to, any number of machines, assuming that there are, number of machines is small enough that the UIDs don't clash, right? But the problem nonetheless is that you still need to have the size of that hash map increases as the number of machines participate, more and more machines participate, right? So let's say if you're using something like a public blockchain, which is, a Bitcoin blockchain, right? And you want to do causal consistency over Bitcoins. Millions of machines, maybe I'm overstating, but almost in tens of thousands of machines participate in a blockchain network. So do you want to, like, in that sense, that each message has to be tagged with a timestamp, which is 1 million entries long. So this is not going to scale, right?
Yes.
So that's another problem, but there are mitigations for that. So there are versions of variants of vector clock that are not as precise, but are nonetheless let you capture some under approximation of causal consistency, causal ordering, but that's for a different discussion. So to answer your question, you can extend vector clocks to any number of machines, dynamically, but then you have the scalability problem.
Okay, but is it also the case that if you're adding new machines and you're maintaining a hash map, that has to be a centralized process? There has to be one process that knows everyone.
No, need not. Because let's say you start with one machine, right? Let's say you are the only machine and you have your own UUID that you've been assigned to you, right? That you know for sure. So you map that UUID to 0 or whatever your local timestamp is, and you map every other UUID that's possible, I mean, conceptually, to 0 or some other, let's say it's 0, because you don't know of any other process, you say it's 0, right? So as the execution progresses, and if there is ever a new process shows up with a new UUID, that's the point when you would know about its existence, and you would increment its time clock, right? It's timestamp. But otherwise, you would just retain it as 0.
Okay.
I mean, conceptually, you start with an assumption that there are 2 power 64 machines in your system, right? So assuming it's a 64-bit UUID. Let's say you start with the assumption that 2 power 64 machines, and except for the machines that you know, every other machine is mapped to 0. And when a machine, as and when a new machine shows up with a new UUID, its stock clock starts, and that's when you know about its existence, and that's when you're going to actually map it to a non-trivial value. Until then, it's just simply conceptually mapped to 0, right?
Okay.
Does that make sense?
Yeah. So in a sense, okay, I think my earlier thought process was that every process maintains their own vector of processes with whom they have communicated, which means that I might be communicating with 3 other processes. Someone else might be communicating in 4 other processes, another one with 10 processes. So the vector representation is different dimensions.
Yeah.
But from your point, it's just, you're saying that we all will maintain a maximum number of dimensions possible.
Yes, conceptually, it need not be physically. The vector, you can simply map everything else that is unmapped to 0 or something. But conceptually, you maintain a vector clock of size 2 power 64.
Mm-hmm. Yeah, but then I think it's just comparing those dimensions with each other's that might be problematic. We'll have to figure it out. There should be some scheme.
Yeah, I mean, you serialize the hash map and send it over, and then there's a way to do it right.
Okay.
So yeah, but that again, it's a very expensive affair. This is well acknowledged in distributed systems literature. You can look up on like how to scale vector clocks, what are the variants, etc. But that's we're not going to discuss that.